Hi there, I'm Errol from Leap Australia, and today we're going to take you through the process of creating a digital twin. We're going to be using the power of simulation alongside sensor data and IoT to extract the most value out of your in-field componentry. Inside this case, we have a Raspberry Pi. A Raspberry Pi is basically just a small computer. On top of the Raspberry Pi, we've included a sense hat, which has a multitude of different sensors. We've also included a controllable fan. When we turn the Raspberry Pi on, a small amount of energy is consumed at the CPU, which generates heat. This heat is then propagated throughout the system. We can increase the amount of heat within the system by forcing the Raspberry Pi to conduct a stress test and consume more power. We can also turn the fan on and off, which gives us more controllability of the temperature within the domain. We're using ANSYS Fluent and Twin Builder as simulation and prediction tools, and we're using PTC's ThingWorx IoT platform to create a full feedback loop digital representation that can track temperatures in real time. By proving that we can use simulation data to track temperatures in real time, we are showing that we can have never before seen insight into our in-field componentry.
So here we have an overview of the full system. The system consists of four major components: the Raspberry Pi, the physical component, our IoT and data analytics platform, PTC's ThingWorx, our systems level analysis, Twin Builder, which is also used to create the reduced order model, and our 3D physics simulator, ANSYS Fluent. Once we've replicated the critical conditions in Fluent, we can use that data to create the reduced order model. PTC's ThingWorx becomes the central hub. It's sending data both to and from the physical component and from Twin Builder. We'll go through each of the four components in greater detail throughout the video. Okay, so this is a copy of the Fluent model. As you can see here, that we've taken the CAD and we've made some modifications, and we've included a fluid volume. So you can see here that we've got our two PCBs, we've got all of the major components modeled, including the CPU and the sensor. So the CPU is where all of the heat will be generated. So there's a volumetric heat source applied in there, and we're tracking the heat as it's propagating through the fluid volume and through the structural volume, and we're picking up the temperature at the sensor as well. I'll show you an example of some of the results. So you can see here that the CPU is nice and hot, and you can see that temperature propagating through the structure. So we've calibrated this model for multiple different conditions: high power, low power, high fan, and low fan. The results of the transient simulations will look something like this. Each one of these result sets from the simulations will be used as a learning condition for Twin Builder's dynamic ROM builder. So this is Twin Builder's dynamic ROM builder. It's a nonlinear ROM builder for multiple input and multiple output scenarios. We bring our learning conditions in from Fluent. As you can see here, we bring it in the form of outputs and excitations. We use these different learning scenarios here to build our ROM. We can then use this ROM to export into Twin Builder and to build our Twin Builder model.
So this is the Twin Builder project. On the right hand side, we have the ROM that we've just created in Dynamic ROM Builder. And on the left hand side, we have a data connector that's connected to an agent which is transmitting information between PTC's ThingWorx and this Twin Builder project. The information that we're receiving from the agent is real-time sensor data from the Raspberry Pi. On one side we have the fan, and the other side we have information about the power. This data is transferred into the ROM, and that ROM tells us in real time what the temperature should be at the sensor and at the CPU. This is then fed back into ThingWorx to be displayed in the ThingWorx mashup.
So this is PTC's ThingWorx user interface. ThingWorx is a rapid application development platform that provides an easy-to-use program for the development of IoT applications. This makes it the perfect tool for developing a digital twin application. ThingWorx already has all of the necessary communication and analytical functionality required built in. On this page here, you can see we have a number of different projects. Our project is Fan Project. In this project, you can see there's a number of different types of entities. The two most important for us are things and mashups. If we go into our Fan Pi thing, you can see that each thing will be assigned properties and alerts, services, and events. In the Properties tab, we can see all of the relevant properties to our digital twin case. These properties will be linked to information coming in from the Pi. They will also be linked to information coming from Twin Builder. Not only are they receiving information, but they can also be sending information as well. We can also use services and events to increase the amount of functionality that we get out of our data. For example, the RPM property contains values coming in from the Pi about the fan speed. We use that RPM value to send through to Twin Builder, and the RPM alongside the CPU load value will be run through the reduced order model. The values output from the reduced order model will be sent back to ThingWorx and assigned to another property. These properties will all be displayed on the mashup that we'll go through next.
So this is what we call a ThingWorx mashup. It's displaying all the important information from the hard work going on behind the scenes by ThingWorx and Twin Builder. The mashup is displaying real-time sensor data from the Raspberry Pi. So we have the temperature at the core, the CPU, and we have the temperature at the sensor. This is alongside the temperatures from the reduced order model. Down on the bottom left, we have the CPU load and the RPM of the fan. These values are being transmitted to Twin Builder. Twin Builder is then using those with the ROM to produce these expected outputs. So now we're going to change the conditions within the Raspberry Pi. We're going to set the Raspberry Pi to high power mode. We should see the CPU percent spike, and we should see an increase in core temperature, followed by an increase in temperature at the sensor. This should be tracked by the twin core temperature and the twin sensor temperature based on this information that's being transmitted into the reduced order model. So you can see that the ROM is tracking really well with the real-time sensor data.
So this is really valuable information. If we imagine that we weren't able to have a second temperature sensor, we are now proving that we would be able to predict the temperature at that point using Fluent. The implication is that with Fluent, we can have a prediction for temperature, pressure, fluid velocity, fluid density at any point in the fluid domain. This is giving us far more information than a couple of sensors ever could, and is showing us why digital twins are the next step forward in industrial progress. Let's not forget that Fluent and fluid simulations are just the tip of the iceberg when it comes to 3D physics solvers. The range of electromagnetics and structural solvers open up a world of opportunity as to the types of digital twins that can be created.